In the circuit, we've got a 30-volt battery. Oops, not 30. Resistance of 120. And an inductance of 0.24. And it says that initially switch 2 is open, switch 1 is closed until constant current is reached. So once that closes, we start off at some sort of zero current and increase to steady state. That means that the inductor has built up its full energy. And then it says that at time T1, switch 1 is opened and switch 2 is closed. So now we've got this happening. So what is the current in the resistor at time T1? So originally the current, when it was originally closed, was going this direction and back to the battery. And then once S1 is closed, S1 is open and S2 is closed, the circuit is going to, or the inductor is going to want to keep the current at from changing, and so it will continue in this direction through this loop. And initially it starts at the current that the original setup ended at. So when it's going through S1, it starts at 0, and when it reaches maximum, we can think of our inductor as a normal wire, and our current is going to be EMF over R, which is 30 over 120. And then when it's closed, so this is IT, then we're going to start at that current, the current it left off at, and we're going to decrease down to 0 as the inductor discharges. So the current in the resistor, right when it flips, at the time that it is switched, is going to be the same current that it ended at in the initial setup. What is the voltage across the resistor at time 1? So the voltage across the resistor at time 1 is going to be IR. And since we established I is EMF over R, then it's just going to be our EMF of 30 volts. I forgot to solve this. We've got 30 volts over 120 ohm resistor. So the current for that one would be 0.25 amps for part A, and then 30 volts for part B. So for part C, it says, what is the current in the resistor at time 1 times 10 to the negative 3? So in this scenario, we're going to use our equation. I'll write it down here, but I think also I'll derive it for you just so that you can see where it comes from, and therefore it won't have to be something that you add to your long list of equations to memorize. But you always, when you're deriving this equation, you start with the Kirchhoff's loop rule. We're going through the resistor. We're looking at the blue current this time, and we're going through the inductor, and we're not going through the battery. So this is all the elements that we have in this loop. And when we solve for our equation, we want to bring the time to the other side, the current to the right, so that we can integrate. So here I've got R dt over L, and we can make that negative. And then we've got di over I on the right side. Then I'm going to integrate this. I'll just do it in front of the negative, and I'm going from 0 to some arbitrary time, and we'll plug in our exact time value later. And then for DI, we're going from our initial EMF, which starts at EMF over, or our initial current, which is EMF over R, to some arbitrary current. So we end up with R, negative RL times T. And then on the right side, we have ln, and our limits are from I to EMF over R. So negative RT over L is equal to ln I over EMF over R. And then we take E of both sides. And so that cancels that out, and we end up with E to the negative RT over L is equal to IR over EMF. And since we're solving for I, we have EMF over R, E to the negative RT over L. Just to introduce this to you because it might come up, tau is R over L, so you can rewrite this as EMF over R E to the negative T over tau, and then solve for L over R later. But this is your long equation that gets you this. Obviously, your I naught is going to be the current that you start with, so our EMF over R, or we established it right here, which is what we got when we derived our equation. So in the end, we're going to plug in all of our values. What I'm going to do here is solve for tau, which is 0.24 over, or let me look at it. Yeah, 0.24 over 120. That gives me 0.002, and then I'm going to plug in all my values. I have 30 volts over, actually I already calculated that. That is 0.24 from, or 25 from part A, times E to the negative, my T value is 1 times 10 to the negative 3 divided by 0.002. So I'm going to calculate that exponent first, and then I'm going to take E to that power. So the exponent I got was negative 0.5. So I'm going to take E to negative 0.5, and I get 0.6 times 0.25, which is equal to 0.15 amps. Okay, so that was, again, if you want to have this memorized, you can plug it straight into the equation, but if you do the derivation, it'll be something that you can apply to any type of circuit, whether it has one resistor or other elements within it. Okay, so answer to that is 0.15 amps. I'll add it in here. The next part is what is the voltage across the inductor at time t. So let's do D here. The voltage across the inductor is going to be IR. And what I'm doing is, based on this equation, my voltage across the inductor is going to be the voltage across the resistor. So since I know the equation for the voltage across the resistor, then I can, that same value would be the voltage across the inductor. And so in this scenario, I have 0.15 and my resistance is 120, which gives me a voltage through my resistor of 18. And you can plug it into the loop rule, but in the end, you're going to get at least the magnitude of your inductor is going to be 18 volts. Okay, how long will it take for the current to decrease to half its initial value? I am going to just take this equation because I already did the long derivation, so I'm not going to do that again. But all I need to do is take I divided by 2, and then I've got I naught is e to the negative t tau. Half its initial value, I can take I naught over 2 because that cancels a bunch of things out. So first thing I'm going to do is I know that the I naught on the left cancels with the I naught on the right. 1/2 e to the negative t over tau is going to give me, if I take ln of both sides, I get negative t over tau is equal to ln of 1/2. And then if I take t is equal to negative tau ln of 1/2, I can plug in my tau value. So I'm going to erase this right here. I got the value for tau down here, which is 0.002. And then ln of 1/2, I can plug that in my calculator. And I get 0.00138 seconds. So let me just divide up this work. This is all for C, and then for D and E, you've got the steps there.